Hello, in this video I will try to explain the Perceptron algorithm. So it's very simple linear classifier. Let's start with the example of the problem is classifying images into faces or not faces. Let's say you have an image and the image contains certain pixels, and you want to recognize if the image is that corresponds to face or not face. So this is just some example. Okay, and so the idea of Perceptron is that let's call this image X, okay, this matrix. So this is, for example, 200 times 200 pixels. And now we want to come up with the axis represents this image, and now we want to come up with function f, scoring function, that takes as input x, and then returns some number, and the number is anything from negative infinity to plus infinity. So just some real number. And the idea there is that you will say, so this image has some corresponding label, y, and the label is either face or not face. So it can take one of these two values, and we don't know what's the label here, so y is something that we don't know. Now the idea here is that if f of x is higher than or equal to 0, then you say that the label is face, and else you will predict the label as not face. So this is the answer that you will return. You will just take this image x, and then you give it as input to this function f, and then if it gives you something positive, then you return face. If it's something negative, you will return not face. So in this example, I will focus only on the face not face, but we will return later to, we'll see later how to deal with when you have more than two classes, like what we do in digits. So the problem now is how to come up with this function f. The idea of this is basically the basic problem of classification in general. Now let's see how we can come up with function f. So the idea of Perceptron is the function f of x is a linear function. So you have some scalars or some weights, w1 times something that we call feature, and I will explain it, feature 1 of x, plus w2 times feature 2 of x, plus until, let's say you have up to 10, let's say you have 10 features. You can have as many features as you want. Let's say you have 10 features, and then you have w10 times phi 10 of x. So what are these w's? These w's are just some numbers. They could be 3, 5, negative 6. So they are just some real numbers. Okay, and the features are characteristics or attributes of this image. I give you an example of the features. So let's say we take this image and we divide it into various regions, cells. So in this case we have 3 times 4 features. Okay, so each one of these regions becomes a feature, defines a feature. So we have then 4 times 3 features, and let's call the first one feature 1. Let's call this phi 1. The second one feature 2, phi 2. Then you have phi 3, etc. You have phi 4 until phi 12. This is the last one. Okay, so you have 12 regions. Each region corresponds to a particular feature. So what does this feature do? Feature is kind of a mask or like some function. it looks into a region of this image and computes something and returns a number based on that. So phi1 is cares only about this part. It's specialized in this region, this corner. Phi2 specialized in second corner. Phi3 in third corner, etc. Of course, this is just an example. Features, you can come up with any kind of functions defined on top of this image. So let's define, for example, the feature as phi1 of x. Let's define it as the number of black pixels, if we are talking about black and white image, in the top left corner. So this is the top left corner, and this feature, what it knows only how to count how many pixels are there, how many pixels are marked. So for example, in this case we have 0. As you can see, when you draw a face, usually there is nothing that appears on the top left corner, and center there is always something, right? So feature tries to get some attribute or some characteristic out of the image. So feature 1 knows only about this corner, and it returns a number. It could be any number. In this case, it's the number of black pixels in the top left corner of the image. And the image here is image X that you care about. Okay, so phi2 does the same thing, but phi2 is specialized in second corner, phi3 is the third corner, etc. So each feature is specialized in certain region, and it computes the number of pixels that are marked. This is just an example. You can divide the image to as many cells as you want. You can consider each pixel by itself as a cell, and then you will have binary features. They will be either 0 or 1, true or false, or you can have other kind of features. So these features are defined, so you write the code for computing these features, which means that given some image, you know how the values of these features. For example, in this case, feature 1 is set to 0, feature 2 is 1, 2, 3, we have 3, feature 10 is also 0, etc. So each feature will have different number. So these features are always known, they can always be computed, they depend on the image. The problem is the weights. How do you weight these features together? Which features are important? And this is the problem of Perceptron. This is what the Perceptron will be trying to learn. It will try to learn the features that are most important, the features that matter the most, and it will give them higher weights. And those that matter less, it will give them lower weights. And it will learn how to add these features together, how to weight them differently, and add them together to give you a single score at the end, f of x. So the problem is how we all know that now if I give you some function x, you know how to compute phi1, phi2, phi t, you just count the number of pixels. The problem now is how to come up with these weights w. So the problem with Perceptron is how to find w, w1 until w10 if you have 10 features. Or in this case we have 12, so we're going to go to 12. So the idea of Perceptron initialize everything to 0 or randomly. That's the first thing you do. Then you start learning, you start training these weights. And the way you do it is you have a data set, you have training data set, and this training data set you have a lot of images. Some of them are faces, some of them, others are not faces. So you have, let's say you have 4 images. You have x1, x2, x3, and x4. You have these 4 images. So the idea of Perceptron is you will be iterating through these images. You first one, then you go to the second one, then third one, then fourth one, then you'll be back all the way to the first one, then second one, third one, fourth one, and you just keep iterating. So you just keep jumping from an image to the next one. And as you are doing this, you'll be updating these weights, W1 until W12. Okay, so the Perceptron starts with the first image. It updates the weights based on that, and I will explain how to do this, but I'm just giving you the high level idea here. So you start with first image, you update all these weights, and then you go to the second image, you update all these weights, and then you go to third image, you do same thing, fourth image. Once you are done, you go back to the first one, then second one, third one, fourth one, and you just keep repeating this until you hit some time limit. You cannot, you say you have some time budget, let's say 5 minutes or 10 minutes, or if you notice that your weights are not changing that much, you see that you are making all these passes, but your weights are remaining almost the same, then you say you converge, there is no point. Or maybe in the ideal case, if you make full pass and nothing changed, then there is no point in going back again, okay? So then you say that you found the weights. Now let's see how do we update these weights. So we take the first image x1, and then what we do, first thing we will compute its features. So of course, we can divide it into the cells. It's the same thing that we did here, right? So we can treat it as in the same way as we are treating any image. So we divide it into different cells. And then we compute the features. So we compute phi1 of x, and then phi2. So this is x1, and then we take phi2 of x2. X feature until phi12. Here we have 12 features. Then we take all these features. So basically, what does this mean? We compute the number of marked cells, of marked pixels inside each one of these cells, the number of black pixels. Then we will multiply each feature by the weight that is associated to it, W1. So each feature has some weight parameter that is attached to it, these famous W's, until the last feature, which should be multiplied by W12. You add them all together, and what you get f of x1, a score for this function x1. Then you say if f of x1 is strictly positive, which means that your Perceptron is predicting phase, and the label is phase, then you are good, do nothing. Or if you are predicting not phase, if you get something negative, right? Because we said that this is how it works. If f of x positive, then your prediction is phase. If it's negative, then you predict not phase. And the label is the ground truth. This is something you know that's used for learning. This is something given to you by humans. So some person went through all these images and looked into them and provided the ground truth label y. It says for x1 y equal is phase, for x2 y is not phase. So if you are in this situation, then do nothing. Do nothing means just move on to you are doing well. So far you are doing well. The image is indeed phase and you are predicting phase, or the image is not phase and your Perceptron is predicting not phase. If this is the case, then just move on to the next image, okay? Skip to the next image, x2. And at x2, repeat the same thing. If your predictions are accurate using the current weights that you have, then move to x3. Of course, these weights, they keep, at a certain point, they will be updated and they will be changing. You always use the most recent weights that you have. Let's see now what happens in the other cases where what you are predicting is something positive. The score that you are predicting for the current image is positive, and the label is not phase. So your prediction goes against the ground truth label. We know that this image x1 is not a phase, but you are predicting a positive score. So what you will do is this, you go through all your weights, it's very easy, W1. W1 becomes the old W1 that you had. W1 is the weight associated to feature 1 that contributed to this wrong answer. So it has to be punished basically, it has to be punished such that it will not be making this kind of errors, okay? Penalized, sorry, that's a term. So W1 is the same W1 minus something. We want to bring it down because the output that we have for f is too high. So we want to decrease the value of f so we can reduce something from W1. And you'll be doing the same thing for W2, W3, etc. So for W1, how much should we subtract from W1? We'll be subtracting exactly the amount given by feature 1 of the very image. So x1 is the image that we are working on right now in the training data. It has a lot of features, as we said, and there is this feature 1, feature 2, feature 3, etc. But W1 is only concerned with feature 1. It has no business to do with feature 2 or feature 3 or anything else. So W1 is the weight that is typically, that is always multiplied by phi1, right? So if you see in the prediction here, W1 is always multiplied by phi1, and then W2 is by phi2, and then when you add them, you get the score. So since the score is too high, it should be negative. The score is too high because the label is not phase. So we should be getting something negative here. W1 should be reduced, and it will be reduced by this amount, by that much, phi1 of x1. So concretely, if for x1, let's say this is your image, and phi1 is the feature in question, and let's say in this image it takes value 0 because there is no pixel inside, then W1 will be reduced by 0, okay, which means it will remain unchanged. Now let's assume that phi1 it has value 5, for example, there are 5 pixels inside this region, then W1 will be the out of W1 minus 5. And this is how we update the weight W1. The same thing is done to all other weights. So you also go through W2, second weight, and you take the previous value of W2 and you add to it the feature associated with W2 in the feature for the training image x1. We are doing all that for x1, for example. And then we will do the same thing for x2, for x3, for x4, until we are done with all our training data. So let's say we had, since we said that we have 12 features, then we have to update the 12 weights associated with these features. Now there is another kind of error that we could be making. The second direction of the error could be that we are predicting that image x1, and of course the same applies to any image in training data that we are learning from. So let's say we are predicting something, a negative score, so we're predicting that it's not a phase, and in reality from our labels we know that actually it is a phase. So in this case we need also to update the weights of the perceptron, the W's. But since the problem here is that they are negative, and we want to increase the value of this score such that next time we'll be getting maybe a positive score and will match with the ground truth data. So what we'll be doing is the same thing, except that this time each weight, so it's exactly the same thing as what you were doing before, except that now you'll be increasing the weights as opposed to decreasing them. So W2 is the out W2 plus the feature, second feature, phi2 of x1, etc. So all the weights will be updated in this way. So as you can see, it's exactly the same thing, except that in previous, sorry, here it should be minus, and here also it should be minus. So in the first case, we are just subtracting the features from all the weights, and second case, we'll be adding the features to all the weights. Okay, so this is how you update your weights, and then once you are done with this, you move on to X2. So you move on into the second training image, X2, you do exactly the same thing. If you are predicting it correctly, then you don't do anything, you move to X3, but if you are making an error, then you need to update your weights W. And then you move to X3, you do the same process in there, and then you go to X4, etc. And then from X4, you go back to X1. You just iterate through all your images until you hit some time limit. And that's it. And then you get your final weights. After that, the weights will convert to certain values, and you'll be using your weights to predict the label of any given image X. So you have some image given to you, you just calculate the features, multiply the features by the weights that you learned from your data, and then you make your decision based on that. So there is a small thing that I didn't say, which is an extra weight that is not multiplied by anything. It's called the bias. It's just added to everything. Let's call it W0. So it's special kind of weight because it's not multiplied by any kind of feature. It's just added by itself. And we call this a bias. And this makes sure that the separation line is free to not pass through 0. It could be, it's more general. This is more general linear equation, okay? So you just have this extra weight, W0, that we call bias. And we also learn this bias in the same way. So you initialize it to 0, so it's the same, it's treated in the same way as all the other weights. It's initialized to a random value initially, and then it's updated as we are predicting the labels of the train image. The only thing about the bias is that the way it's updated is a little bit different from previous ones. So W0, whenever we will be increasing all the weights by their features, W0 will be, or when we are reducing the weights by their features, W0 will be reduced by 1. So it's always reduced or increased by +1 or -1. And in the case where we'll be updating the weights by adding to them the features, W0 will be increased by adding to it +1. Okay. So you see the only difference with the bias is that it always goes up by 1 unit or down by 1 unit. And that's it. And whenever all the weights are updated, when you update the bias, you reduce -1. In the case you are making this kind of error, or you add to it +1 in the case you are making the other kind of error. And basically that's it. So let's talk now about this is all you need to know for training Perceptron to predict binary labels, face, not face, for example. After this process, you will have your weights at the end. Let's talk now about the case where you want to do more than one class. You want to predict digits, for example. So in the case of predicting digits, you have again, so Perceptron for multi-classes, for multi. So again, here you have some image, and this image, let's say it corresponds to some kind of digit. The image is called X. We can use exactly the same kind of features as we use we use actually exactly the same kind of features. You can also use other kind of features. So you discretize your image into regions, and each region would be a feature, phi1, phi2. So this is the same as what we were doing with faces, predicting if the image is face or not, until let's say phi. Let's say here I use 4x4, so we have until 516. My resolution is 4x4. So the only difference with previous case is in the previous example we had a single set of weights, a single vector W1, W2 until W12 and W0 also. In the multi-class situation, we can have, for each digit we'll have separate perceptron. Okay, so you will have for digit 0, we'll have a perceptron that we call F0 that takes as input X and computes W00 plus W, the first weight of the associated with the first feature, plus W2 0 for second feature, plus W3, the third feature. And the reason I'm adding this 0 here is because I want to distinguish the weights between the weights associated to different digits. So what I'm saying here, these are the weights for detecting digit 0, if this image is 0. And then you have something for digit 1 as well. So you have another perceptron, f1 of x. And this f1 of x is specialized in recognizing digit 1. It gets a higher score when this digit is actually 1. So you can have the bias again, but I'm adding 1 here to say that this bias is different from the bias that I'm using for digit 1. And then I have the first weight associated with first feature of the image. The first feature is, like, for example, this region. But I'm adding also this index 1 on the top to say that this is related to digit 1 and not 0. These are separate. And then you have second weight for digit 1 as well, etc. until W16 for 0, 5, 16, x. All right, and then we have the same thing for digit 2. We're gonna have f2 of x until digit 9, where we have f9 of x. And each one of them is perceptron defined by different weights. Now the problem is how to train these weights. It's slightly different from the way you train when you train the perceptron for faces. In this case, you go through your training data the same way. So it's the same thing. You go through all your images one by one, and you predict the label, and they will explain how you predict the label. If your label, the predicted label matches with the actual known label for this image, let's say it's an image of 3 and you are predicting digit 3, then you don't do anything. If you are getting it correctly, you move on to the next image. If you are predicting something wrong, then you have to update your weights. So in the case your prediction is correct, then you don't do anything. So let's say if the question now is, how do you make your prediction? So the predicted label or predicted digit is the one that maximizes, so among all the digits from, let's call them I, or let's call them y, in 0 until 9, it's the one that has the highest activation. So you take your image and you take the perceptron on the first digit, f0, okay, that we defined here, and you compute the score, and then you do the same thing but using the second perceptron, the perceptron associated with digit 1, and you compute the score. Then you compute the score using the perceptron specialized in digit 2 until you compute the score for the using perceptron specialized in digit 9. And then you pick your best answer, the digit that gives you the highest activation, the highest result, f of y, for y from 0 until 9, and that would be your predicted digit. Okay, so let's say, for example, for this image 3, I'm gonna run it through f0, get some score, run it through f1, get some score, f2, etc. And let's say, for sake of the argument, that f1 is the one that has the highest score, which means that my perceptron will predict label 1 for this image, which is wrong. So if we predict the correct label, we don't do anything, we move to the next image. But if we predict something wrong, then we need to update the weights of the perceptron. So let's say, assume that predicted label is 1 and true label is 3. So what you do is you need to update the weights associated with 1 and the weights of the perceptron associated with 3. So we have also another one for 3, of course. We have for each digit a separate perceptron. So for this is what we will do. I will explain. So assume this is a situation where we are predicting 1, but the real label is 3. What I need to do is very easy. I would go to the weights associated with the label 1, and I'm going to reduce them because they shouldn't be the highest. They shouldn't give me the highest score with this particular image. Okay, so we will do this. I will go to all the weights associated with label 1, that is giving me the highest score, and I will reduce them all by the features of the image set, which means in practice you have to take the first weight and subtract from it the first feature, take the second weight, and the second weight still with the of the perceptron specialized in recognizing digit 1, and you subtract from it the second feature, etc. until, in this case we said we had 16 features, so we go until the 16th weight and we subtract from it the feature, 16th feature with this, and X is the training image that we are processing at present time. And you do the same thing, of course, with the bias associated with digit 1, you subtract from it a unit. So this should be the weights associated with 1 should be penalized because they are too high. Now the weights associated with digit 3, which is the real label of our image, should be rewarded or encouraged or increased, such that next time they will get it right maybe. So we add to them all the features of the image. So you go through all your features, all the weights associated with digit 3, and because you missed this digit, you didn't predict it as the highest score, the weights attached to this number 3, digit 3, should be all increased or augmented, including the bias, of course, of digit 3. That will go up by 1 unit. You repeat this process, so you just repeat this process over time until through all your data until you either hit some time limit or there is not much change happening, and then that's your perceptor.